Hi students, so today we are going to discuss propulsive efficiency. This is lecture 80 in our aerospace engineering course. I am Dr. Ranjan Ganguly. Now this concept is very important because the different type of propulsion systems we have studied, for example the turbojet, the turbofan, the turboprop, the propeller, the ramjet and the rocket engine, they all generate different amounts of thrust. Now the main aim in all these engines or propulsion systems is to create trust, but the price you pay is that some of these are more efficient than the remaining ones. So we are going to define this concept of propulsive efficiency today, and then we are going to look at each of these engine configurations and see which is more efficient, which is less efficient, and so on. So let's start by looking at a very generalized schematic of jet propulsion, which is that the air comes in to the inlet at a velocity v infinity and it leaves the exit at a velocity v subscript e, and inside the jet engine somewhere combustion takes place of the fuel air mixture, and so what happens is that the velocity of the air coming in is imparted an extra velocity or an additional component, and so ve is typically much larger than v infinity. So that's how the jet produces the thrust. Now there are some things which of course are going to happen because you have produced this thrust. Now one of them is of course you have expended power, and this is power which you need because this power is dependent on the available thrust. But something else has happened is that if you are somewhere far behind the jet or at some distance behind the jet, you are going to see that there is this excess velocity which is there. So this velocity Ve minus V infinity has been imparted to the surrounding air, and essentially to some extent this velocity has been lost because the kinetic energy associated with this particular velocity, this is going to be out there, and this unfortunately has been lost. Now we can say that there is a power associated with this particular velocity, and this power is going to be half m dot Ve minus V infinity square. So that is the delta change in the velocity between the exit and the inlet, the square of that into the mass flow rate which is going through. So because we are taking the rate here, we can say this is power. Now this power is something which we actually do not want to have much of, or at least we want to have as low of this PW as possible. And of course we want to have a high value of PA because that of course is giving us TA here. So that's the objective of this particular problem. So before we get into how to do that, let us define certain concepts. So let's go to the thrust equation which we derived in one of our previous classes for the turbojet, and we are going to dramatically simplify it for our conceptual study. So we are going to say that this part which involves pressure is relatively small, and also we are going to say that the m dot fuel part here in this term is also very small. So we are simply going to say that this m dot here is simply m dot air, or we are going to just refer to as m dot when we know that m dot equals m dot air. So with this particular nomenclature, we can simplify this equation to its basic essentials, and so we get TA is m dot Ve minus V infinity. So the first term involves m dot coming from here into Ve, and the second term is minus m dot into V infinity. So that's actually a simplified version of the available thrust which captures the basic premise behind how thrust is generated. And what you can see here from this equation that there are two things you can do. If you want to generate higher thrust, you can increase m dot, or you can increase Ve minus V infinity. So these are the two things you can do. So now we'll define the concept of propulsive efficiency, and this essentially means that there is a particular value that we denote by eta subscript P. This is useful power available divided by total power generated. Now of course the useful power is dependent on TA because TA is something we are trying to create for this flight vehicle. So PA, or the useful power, would be TA into V infinity, and of course that is the power wasted, and that is going to be half m dot VE minus V infinity square, because this particular increment of velocity VE minus V infinity, which is out there in the wake, that was really not very useful for us. That is simply speeding up the air behind the engine, and that is something which is really being wasted. So now we can write the definition. So we can write that eta P is TA V infinity divided by TA V infinity plus half m dot VE minus V infinity squared. So that's the definition of the propulsive efficiency. And of course here we are assuming that m dot equals m dot air. Like I discussed in the previous slide, we are neglecting m dot fuel as being very small. It's typically 5% or less, so this assumption is kind of justified. So now we are going to simplify this expression and see what we get. So to simplify this expression, what we do is we use the fact that TA is m dot VE minus V infinity, and we immediately substitute that into the expression for eta P. So we get this expression here. Now I can cancel various terms. I can cancel all the m dots here. I can cancel one of the VE minus V infinities here. So this m dot VE minus V infinity would go. This m dot VE minus V infinity would go, and here I would simply be left with half and VE minus V infinity. So the square would go here. So this simpler expression is now obtained. Let's simplify this further. So let's take this expression, and we can see there are so many V infinities on the numerator and denominator. So let's divide both these numerator and denominator by V infinity. So we get this particular equation here. Now what we do is that we expand the denominator term, which I have done here. So here you get one term VE by 2V infinity. Here you get minus 1 by 2 or minus half, because these two V infinities cancel out. So now I take this expression here and I can further simplify it, because 1 minus half is going to give me half here. So now I have this expression, and I immediately realize that there is a 2 here which I could send up. So I send the 2 up there, and then I get the much more compact equation here, which is very important and which we are going to look at deeply today. That is eta P, the propulsive efficiency, equals 2 divided by 1 plus VE by V infinity. So now we are able to express the propulsive efficiency completely in terms of two velocities, which are the velocity at the exit and the velocity at the entrance, which is coming in, or V infinity. So let us take a look at this equation and try to understand some aspects of this equation. And we can immediately see that if we want the best propulsive efficiency, then VE equals V infinity is the good point, because at that point, if you see here, VE by V infinity would be 1, so you would have 2 by 2, and then your efficiency would be 1, which is the best possible value, or it is 100% propulsive efficient. But unfortunately, we see that if we plug VE equals V infinity in the thrust equation, the thrust available is simply going to be 0, because thrust available depends on how much velocity increment you gave to the flow coming in. And unfortunately, therefore, this is a completely theoretical case. It doesn't have much practical value, because from the other equation which I have put in blue, we can immediately see that if you want to maximize thrust, which we often want to do in any engine situation, then VE must be substantially greater than V infinity. That's the thing we would like to have. But in that case, what would happen if VE is much greater than V infinity? Then this term is going to be large, and therefore the efficiency is going to be, unfortunately, quite less. So let's quantify these numbers for some physical feel into this problem. So here what I have taken different values of VE in terms of V infinity. So of course we discussed this particular trivial case before, where VE equals V infinity. In that case, TA became 0 and eta P was 1. Now let's take the case where VE is twice of V infinity. That means you are doubling the intake velocity at the exit. In that case, TA would be m into V infinity, and what would happen is that eta P would be 2 divided by 1 plus VE by V infinity, which would be 2. So 2 by 3, and that would give us 0.67 here. Similarly, we can try VE is 3V infinity, that gives me these values. So again, the thrust available becomes larger, but my efficiency goes down further. If we go all the way to VE is 99V infinity, then we get a very high value for thrust, but we get a very low efficiency here. So you can really see that there is a trade-off issue here. That means we need to find some middle ground based on our requirement so that we accelerate the velocity coming in, but we should make it such that the acceleration is not too large. Now, in case we want a very high amount of thrust, then of course there's nothing much we can do. We may have to live with the lower propulsive efficiency figure. So let us now revisit all these particular engine configurations and look at what happens there. So if we look at the turbojet, the velocity comes in and then it goes out of here, and typically turbojets work on the principle that VE is substantially larger than V infinity because they create a lot of thrust. And of course you can see from this that it's not going to be very efficient. Now let's look at the turbofan engine case, and here you are seeing that some of the air is actually thrown out from these locations here. So there is a location between the shroud and this casing here, and so air is going to go off here. Now this air which goes off is actually quantified by something known as the bypass ratio. So that is the mass flow outside the core divided by mass flow through core. So you can see here that a lot of air will go out. So most turbofans have a bypass ratio of 5 to 10, and increasingly the newer engines which are being produced have a higher and higher bypass ratio. Now at the extreme of this particular concept, you would create something like a turboprop where most of the air is actually going in this direction. So in these cases the mass flow rate is actually higher, so most of the air is going here. This may be up to 50 to 100 times the air going into the turbine here. So in the case of turboprop, that's quite a large amount. And of course here the slipstream is not so clearly defined as in the previous case because there is no shroud here. This is kind of an open system as far as the upper and lower bounds are concerned. Now, of course, then we go to the other extreme, which is the ramjet. The ramjet completely depends on a very high exhaust velocity. So, a lot of this velocity is going to be imparted to the air, and therefore you have a very large V E minus V infinity term, and therefore you are going to have a lot of wasted power. So, again, the efficiency of the ramjet is going to be pretty low because the exit velocity is much higher than the entering velocity. Now finally we look at the rocket engine where actually the entering velocity is almost close to zero, and so what happens is that there is a huge increase in velocity from the gases from this point to the exit point here. So VE we can say is extremely large compared to V infinity, so certainly the efficiency of the rocket engine is going to be extremely low. So we can now make some comments about the different propulsion systems. We can say that the propeller is a highly efficient system. So now why is the propeller not used in all places? One of the problems is that the propeller wing tips or rotor tips encounter sonic velocity at high forward speed. So that actually limits some of their use. Now we also saw the turbofan is going to be very efficient, and this actually has emerged as the compromise solution for most of the commercial jet type of situations, and here bypass ratios between 5 and 10 are being used. So increasingly the engine manufacturers always try to have turbofans with higher bypass ratios. So in the old days it used to be about 5, but nowadays you are getting bypass ratios like 9 and 10 also. Now turboprops are also very efficient. They have bypass ratio of 50 to 100, but the problem here also is very similar to the propeller, is that the rotor blades may encounter sonic velocities even though your forward speed is much less than the sonic velocity. So you can be susceptible to various kind of compressibility effect, waste due to that, and also related separation and shock waves and so on. Now, of course, we see that the less efficient propulsion systems are the turbojet, the ramjet, and the rocket engines. And as you would expect, the turbojet and ramjet are often used in military type of applications. For example, if you are making fighters, you may go for a turbojet. When you are doing things related to national security, costs are not so much an issue, so those things may not matter. You are mostly interested in performance and power. The ramjet is also quite inefficient, but do remember the ramjet is often on a one-way mission, so it really does not have any costly parts and so on. So in a way, whatever you are expanding in terms of fuel, you are saving in terms of all the parts you need to put in. And since this is a vehicle which is often used on a one-way mission, you don't bother too much about the costs over a lifetime, which you would for a commercial jet. Now, finally, we saw that rocket engines have very low propulsive efficiency, but of course, you need to use rockets in certain situations, such as if you are going to space, if you are planning a moon mission, if you are planning a Mars mission, Jupiter mission, or Saturn mission, then you will need to use rockets. So, in that case, there's nothing much you can do because you are carrying the oxidizer, the fuel. It's basically going to start off at a very low velocity, and therefore, the increase in velocity is very substantial, and so propulsive efficiency is going to be low. So at the end of this lecture, do remember these two equations which are extremely important. One is that the propulsive efficiency is defined as 2 by 1 plus VE by V infinity, and also that the thrust is m dot into VE minus V infinity. So if you do remember these two equations, you will very clearly know the trade-off between propulsive efficiency and thrust available. You clearly see that VE must be greater than V infinity, which is required for thrust, and the greater it is, the bigger it is, the worse the propulsive efficiency is going to be. Now, one more philosophical aspect is that it's better to impart a small velocity change to a large mass of air for propulsive efficiency, and this is something which is certainly seen in propellers. It's also seen in turboprops and turbofans, and as you try to accelerate the air at a greater and greater velocity and you have a smaller mass of air, your propulsive efficiency is going to certainly decrease. So that was the lecture for today, and with this I think we have concluded the propulsion part of this course, and I think there's very little content left, at least for now. So I think in my next lecture I'm going to talk about hypersonics, a brief definition and discussion, and then we are going to end this course, at least formally for now. So I'll end this lecture now and I will see you in my next video. See you then.